Hello guys. So in the next video, in joins topic, so we want to talk about bearing pads. So bearing pads is used to distribute concentrated loads. So when you have a point load, concentrated load like this double T flow, so you want to distribute the concentrated load to prevent spalling, prevent direct contact. So the bearing pad allow limited horizontal and rotational movement. So there is some rotational movement uh, allowed by the bearing pad in term by some deformation of the pad. Through deformation of the pad, it allows a slight horizontal and rotational movement, and it prevent direct contact, concrete to concrete, which could lead to spalling or reduction of effective cover to the reinforcement. So the supporting members will be more protected by having these bearing pads. And bearing pad is used when dry or wet bedding mortar is not practical. So if you want a higher bearing capacity, then you want to opt, you want to choose bearing pads compared to dry or wet bedding. So their main use is supporting double T floor units and long spans beam, where the end rotations might be quite large. So usually they are used for this T beam, a single T or a double T floor. And its typical size would be 150 times 150 mm, and length or breadth of the pad should be 5 times its thickness. And for flooring, it is um, suggested to be 6 mm, and other than that to be for beam will be 10 mm minimum thickness. So your length will be 5 times of the thickness. So if it is 6 mm, so you need 30 mm of length of pad. It is made of rubber or synthetic rubber, a neoprene, or with lead or steel reinforced. As you can see, there is a steel plate reinforcement inside the uh, synthetic rubber. A composite sandwich pads reinforced with thin steel plate sustain higher load. It will sustain higher loads. So hardness of rubber, the unit is Shaw, will be between 40 to 70. So usually when you are submitting for material approval to be used, your bearing pad to be used, you need to be submit for approval, and then that will be tested at RRIM, Rubber Research Institute Malaysia. So it will determine your hardness value, durability of your rubber, and mechanical properties also. A limiting compressive strength for rubber is taken as 7 to 10 Newton per millimeter square. To behave satisfactorily, it needs to deform evenly. So you need to deform evenly, and laterally you need to deform even and in lateral when load is applied. So you wouldn't want a deformation like this. This indicates a rotation, so your deformation is not even. It deforms laterally but not even. A lateral deformation is resisted by either the interface friction. So lateral deformation is prevented by the friction. So there's a friction here resisting the deformation, and then the internal tensile reinforcement, that is either your pure synthetic rubber or steel reinforcement. And interface friction depends on the loaded area, the size of the bearing pad, as given by the shape factor. So the area define the internal interface friction. So if the pad is infinitely long, so your shape factor S will be bearing length divided by thickness, where T is the original thickness. In the case of isolated pads, so your shape factor will be length times width divided by 2 times T thickness times the length plus the width. S should be more than 2 for floor units. For floor units should be more than 2 and more than 3 for beams and rafters. So if it is a double T floor, so the value of S to provide for shear friction is should be more than 2, and for beams and rafter, which is more critical, the shear the friction will be more than 3 the value. Eccentricity of the load E, which is equal to moment divided by force, axial force, vertical force. Moment divided by force should not, the normal force N normal and moment should not exceed 1/6 of the bearing pad breadth. The middle third rule. So it should not exceed the 1/6 of the bearing pad breadth. So if it is 60 mm breadth, so the eccentricity should not exceed 10 mm. Where the rotation theta is known, then you can calculate the deformation delta t by multiplying with 0.5 times bearing length and times the rotation theta. So the positive value, we have plus minus, the positive value is at the leading edge, and the negative value will be at the rear edge, the front and the back. The positive will be at the front. Where you increase the shape, the negative will be at the positive, it should be negative, so you have a rotation there due to your eccentricity. So Precast Concrete Institute PCI limits rotation of unreinforced and random fiber elastomerics to be 0.3 times thickness divided by breadth. So this is the graph for three types of bearing pads. We have gummy sponge here, and then bearing pads with 40 shore, and then bearing pads for 70 to 60 70 shore. So your deformation here, theta t, is based on this strain value, strain value, which is delta t uh, divided by t. And then your shape vector is a naught divided by t, and then your compressive stress is normal force divided by a naught. Is the shape, the this value, the original area. So what basically this graph tells you is the you can take for example, you have a compressive stress based on your normal force you get in your original area. So you get your compressive stress here. Let's say is 3 value, so your strain would be 0.2. And you get your 0.2 here based on your thickness. For example, your thickness is 6 mm, so you get this value delta theta. So you need to comply with the rotation and so on. So let's take a look at example here. Example 8.6, a double T floor. So it's a double T floor unit is simply supported. So it is simply supported over effective. This is your span. Span is 11 meters, carries uniformly distributed loads of 10 kilonewton meter live load and then 5 kilonewton meter dead load. The self weight of unit is 7.8 tons, so 7,800 kilos. And the floor unit is supported on 150 times 150 times 6 mm. Bearing pad, unreinforced rubber bearing pad of hardness 60 shore. So this is your um, character of your bearing pad being provided. And then determine the maximum and minimum deformations of bearing pad. So you want to know the delta t, the deformation. Check the shape factor as the PCI recommended limiting rotation this value, is it comply with the rotation, we're well below the limited rotation, and the permanent dead stress limits. And the flexural stiffness of the floor unit may be obtained using I is given here, moment of inertia, area moment of inertia, and then your EC value is 15 kilonewton per millimeter square. So that is your EC value. So your EC value is your elasticity modulus of the concrete. So your EC value is given as 15 kilonewton meter millimeter. So this is your modulus of elasticity for concrete. Then your shape moment of inertia based on your double T floor units. So first, we calculate the shape factor as limited by repeat as limited to be more than 2 for floor units. So we check using this equation. So this is your BL, this is your BP, this is your T, this is your BL plus BP. So if you calculate, you get 6.25, which is over 2, then it's okay. Then you calculate the ultimate load. This is your live load is 10 kilonewton per meter. Then your dead load is 5 kilonewton per meter. So and the self weight is 7.8 tons. So this is your live load. This is your dead load, UDL. So it is being simplified in this solution. It is acceptable for me. If you simplify, there's no, as you can see, there's no multiplication with the weightage as recommended by BS. It can be either one. So you can so this is your live load and plus dead load times by your span. This is a span, and then plus your self weight. This is self weight 78 kilonewton. So you get the total load, total ultimate load W, which is equal to 243 kilonewton. So as this is a double T floor, so you have a 4 support, double T floor here, shown here. You have 4 support here, 4 bearing pad. So it is simplified to be divided by 4 here. Disregards the distribution of the area. So you divide it by 4, you divide it by 4, then you get 60.75 kilonewton. And then this ultimate load divided by the area of bearing. So you get your compressive stress. So based on this compressive stress, you can get your deformation strain. As you can see here, you have your uh, compression stress here. This is in the example 2.7. So around here, so you get your 60-70 shore. So based on the figure, you get your value of strain is 0.2. From the 0.2, you can put into equation here of delta T. This is your equation for delta T, 0.5 plus minus 0.5 times BL times delta. So you get your 0.2 times 6 only. Uh, we use this equation first to get the delta t. So we don't know delta t yet, so we need to calculate delta t. Delta t is equal to strain divided by strain times delta, strain times thickness. So strain times thickness, you get your delta t. So this is your strain, this is your thickness of the bearing pad. So you get your delta t. Change in thickness would be 1.2 mm due to compression, because this is compression force, compressive stress here. So end rotation of a simply supported member. This is an equation that we have already learned in strength of mechanics. For a simply supported load with length of L and elasticity, modulus of elasticity for concrete is EC, and uh, moment of inertia of I. So you get your theta here, delta, your rotation. So the maximum rotation. So this is your W. So this is your span, length squared. This is number integer 24 based on the equation. Times EC, this is given. This is your EC. This is your I. So ensure the unit is right. So unit is Newton per millimeter. This is kilonewton. This is this is millimeter. This is in millimeter. This is in millimeter power 4 ni. Give me millimeter power 4, and then this is in kilonewton per millimeter. So basically the unit should be consistent, so you can cancel out and calculate value with consistent unit. So as we talked about earlier, PCI limits your rotation should be 0.3 times thickness divided by BP divided by B. So maximum rotation will be 0.012 radians. So currently you're calculating it is 0.093 radians, so it is okay, complies. If not, you will need to change your joints to become a moment resisting joint. And then delta t, you can, based on this value of radians, you can calculate delta t, change in thickness, 0.5 times 150 is your BL times delta. Using these equations, you get the delta t. So input your theta here, so you get your 0.7 mm due to rotation. This is due to rotation. Last time we checked, the deformation is due to compression. So based on these two deformations, the total up, you get your maximum deformation. So deformation due to rotation, and then the deformation due to compression. 1.2 compression, 2.7 is due to rotation. The total up, you get 1.9 mm, which is less than the thickness of the bearing pad. So it's okay. So minimum deformation delta T 1.2 minus 0.7. This is we as talked about earlier. So you get your positive and negative maximum and then minimum deformation. So your minimum deformation minus the thickness is reduced by 0.7. So your deformation total up deformation will be 1.2 minus 0.7. You get 0.5 m, which is more than 0. So you have a balance of thickness here 0.5 mm, so it's okay. So then the full bearing pad is active. To determine we want to determine the permanent stress resulting from the dead load of 133 kilonewton. So the dead load of 133 kilonewton, as the name implies, the permanent dead stress limit from the question, permanent dead stress limit, you will consider only the dead load and self weight. So you have your 78 self weight kilonewton, and then you have another one is your dead load, which is 5 kilonewton per meter, uniformly distributed, and then times the span will be 11, so 55 by 78, you get 133 kilonewton. So the stress resulting from the maximum strain of 1.9, so this is your maximum max from here, maximum load. Maximum strain, so maximum strain is the maximum deformation divided by your total thickness. So 1.9 divided by 6 is 0.32, which is based on the equation 0.32 around here. So you get your 4.6 around here. So 4.6, about that 4.6 near maximum compressive stress as the proportion of the dead load to the total. So this is a proportion 0.55. This is total load. This is the dead load 0.55. The corresponding dead stress is equal to 0.55 times this is your maximum stress. This is your maximum. This is the compressive stress. So we take a proportion because this is not a total value. This value 4.6 is based on total, based on total force. So we take a proportion of 55% of the total stress. You get 2.5 Newton per millimeter square, which is less than 3.5 Newton per meter square of a recommended maximum. So which is less than the recommended maximum permanent dead stress limit. So that will be all on this compression joints. So for your deeper learning, you can take a look on shear joints, which is widely used, especially in segmental box girder shear keys. And then we have tension joints, pin jointed connections, and then lastly, moment resisting connection. When you are not, you need to resist a larger moment instead of bearings. Instead of using bearings, you can do a cast in situ moment resisting connection. So I see you in the next video. Thank you for your attention.